Swayam Prabha. Digital India. Educated India.
In this lecture, we will complete our discussion on particle image velocimetry. We start with the discussion on light sheet optics. You can see that there are lenses which are arranged in order to get us an appropriate light sheet, which would help us to illuminate the tracer particles as they move along with the flow. Now, the essential element for generation of the light sheet which will illuminate the tracer particles is cylindrical lenses, and you need to have one so that you can form an appropriate light sheet which is well focused and of the desired thickness with the set of lenses that you will be arranging. Now, when you have a very small beam diameter and small divergence, as in argon ion lasers, only one cylindrical lens can do, and that can give you the appropriate light sheet. However, in ND-YAG lasers and other light sources which are more common in PIV applications, we usually need a combination of different lenses, because the beam that is emerging out of the laser is not all that small in diameter, and the divergence may be of a greater order. And then you finally need thin light sheets of high intensity. The combination of different lenses will achieve that for you. At least one additional lens has to be there for focusing the light to an appropriate thickness. So, you start with a cylindrical lens and then add on one more, so that the thickness that you have originally is well controlled after the second lens, and then you go for a third cylindrical lens which generates the light sheet of constant height. So, here you are looking for a light sheet of constant height, minded that this is the side view, while this is the lower view is the top view. So, in the side view you are getting the height of the light sheet, while in the top view what you get is the thickness as is indicated here. And the focal length of the lens system that you have has to be appropriately adjusted. And why you need a diverging lens to be used first is that the focal lines should be avoided. What happens if focal lines are generated? Especially in high power pulse lasers, the focal points have to be avoided, because at those locations the medium gets excessively heated, and focal lines may not ionize the air, but they would certainly burn the dust particles which are there in the medium, and you need to cover that region well through which the light sheet is moving or evacuated, so that you can avoid such happenings. And of course, using a diverging lens reduces that problem to a significant extent. Why this needs to be avoided? It is because the beam properties would get significantly altered because of the acoustic radiation which emerges if the dust particles are getting overheated and burnt. Therefore, that is going to create aberration in the beam and the light sheet properties and degrade it, which needs to be avoided. We move on to cameras. In PIV, what we notice is that broadly there are two classes: high speed film cameras and digital cameras. Again, digital cameras are more widely used these days. In the world of digital cameras, again you have two categories: charged coupled device based cameras or CCD cameras, and complementary metal oxide semiconductor based cameras or CMOS cameras. Beginning with CCD, it is basically an electronic sensor that can convert the incoming stream of photons into a stream of electrons. And the CCD sensor essentially comprises of an array of individual CCDs, which are arranged in lines or rectangular arrays, and individual CCD elements in the sensor are called as pixels. You can accommodate typically 100 pixels within a millimeter length. In contrast to the CCD pixels, in CMOS sensors you have photodiodes which can be controlled separately by certain transistors, and you can achieve better sensitivity and relatively low noise. The active pixel architecture which is used gives individual access to each one of the pixels, and this could be a very big advantage in the sense that you can integrate some fundamental camera functionalities like amplification, controlling the number of pixels to be active based on the region of interest, or allowing higher frame rates in trade off with image resolution, etc. Also in the IR wavelengths they are more sensitive. In high speed cameras also they are better preferred because they can offload the footage quicker than the CCD cameras. So, you have to weigh your advantages and disadvantages when you use or choose a suitable camera for the PIV application. Moving on next to post processing of the raw data. So, what do we mean by raw data? Essentially, raw PIV data is available as a stream of images or frames which comprise of a dark background in which numerous small brighter spots are visible, like the one you see over here. And again, if you recall, in our earlier discussions we have said that neither should the particle density be too high or too low. A medium density is what is preferred for PIV applications. And what you see as the brighter spots, of course, are the instantaneous positions of the tracer particles which are getting advected by the flow. By correlating the image information between two sequential images, the displacement in a vector sense, which includes both magnitude as well as direction of the individual particles, can be obtained. Once you get the displacement vector, you can divide that by the time interval between the two frames, which is usually small. The velocity vector for each particle over that time interval would thereby be obtained. If you are making a measurement in steady flow, then you can expect that the vectors won't remain, the vectors would be remaining invariant, they won't change. While in unsteady flows, as the time elapses at a given location in the flow field, the vectors may be changing from time to time and quite dramatically. In practical applications, when we say steady flow, we do not really mean to say that the steadiness is going to be there up to the microscopic levels anyway. The steadiness is broadly in the macroscopic sense. So, there could be local small changes even in a broadly steady flow. So, there could be minor variations in the velocity vector at each location, but they are not as significant as in an unsteady situation. So, we need to understand this distinguishing factor. We recall about this small sketch that we had looked at the beginning of the lecture, which initiated the section on particle image velocimetry. So, there we had talked about the entire image plane and then trying to break it down into small sections called as the interrogation windows, and looking at the interrogation windows at different instants of time and trying to figure out the particle movement by referring to two juxtaposed frames. When we look at different ways of analyzing this picture, there could be different kinds of techniques deployed. You have a single frame technique, where in a single frame you look at the particles over a certain time corridor and you keep looking at them through the entire corridor. So, the particle essentially traces a path during that period and you get a kind of a streak. In the single frame itself, if you had illuminated it by giving some laser pulses and opening the camera over a short period of time when the region was illuminated, then you would see the same particle at two distinct positions at the two time instants, which gives you a double exposure in the single frame. On the other hand, you could use multiple frames and again look at the same particle. For example, here you have a double frame single exposure, where the same particle at t was here, at t dash is observed over here. Again, in multiple frames you could have it like the way it is shown at the lower row. We try to take it forward and apply the spatial cross correlation analysis, which is basically the tool used to give you the finally the velocity vector information. We are looking at two frames essentially. What are they conveying? They are showing us the instantaneous particle locations in an interrogation window at two instants of time. Let us say this is time t and this is t dash, where t dash is of course t plus delta t. You see a number of particle images in this frame. The same set of particles have moved, have relocated, and the hollow positions are essentially indicating their corresponding positions at time t, while the filled positions are their current positions. For a given particle image in the first frame, let us say you talk about this as the particle P1. Each particle image in the second frame is a possible match candidate, and each pair represents a possible displacement with equal likelihood, which means that you might map this P1 to particle locations which are available at time t dash, and all of them are equally probable to begin with. Now, this possibility is represented here with a frequency histogram or displacement histogram, where each peak represents a possible displacement, and all peaks have equal amplitude to represent that each match pair has an equal probability. Therefore, the amplitude information is connected with the probability. Now, this procedure, like we did for the particle P1, it can be repeated for all the remaining particles, let us say P2, P3, P4, and let us say up to Pn. So, this procedure once repeated for all the particle images, and the probabilities in the displacement histogram are now superimposed with all those possibilities being calculated. The displacement peak for each of the matching pairs become dominant over the displacement peaks for unrelated pairs. So, now we will see dominating peaks instead of peaks of equal amplitude, where we started from. For example, here you see a very sharp peak, and there are others which are sharp as well, but there are much weaker peaks as well, which will now be filtered out as improbable events. Based on that, you can now develop the velocity vectors by picking those peaks which are the dominant ones, and therefore mapping the initial position of a particle to the subsequent position between the two frames. Velocity vectors are now calculated based on the displacement of matching pair particle images divided by the time interval between two interrogation window frames. So, in general, if you have I particles, then each particle will have a corresponding displacement, let us say delta L I, and that needs to be divided by delta t, so that you get the velocity associated with the particular particle. So, this is in essence the idea of the cross correlation analysis. We are not getting into the details of the technique, but broadly this is the idea. Another very important aspect of the whole process is the synchronization. There is usually a piece of hardware which is called as the synchronizer. It controls the timing of the laser illumination and the camera data acquisition. There is a timing diagram which can be configured by the user basically, and the timing diagram is also dependent on the sensor that you are going to use at the camera end. So, different kind of CCD sensors, for example, use different kind of timing diagrams, not that you can change the entire configuration on your own, and you can thereby end up setting a profile for the camera frame rate acquisition and a profile for the laser light pulses. So, the peaks over here, for example, are indicative of laser light pulses, the specific instance at which they would be pulsing. They are short instance within which the tracer particles will illuminate. Again, the camera will remain open for some time to capture that image and then again close. That is the kind of synchronization that we are talking about. So, at the computer end, you are going to configure the timing diagram. The synchronizer is thereby commanded by the computer. Accordingly, it triggers the laser illumination and the camera acquisition. Let us look at simple examples where all this is put together. So, here we are looking at an experimental setup for a flapping wing. There are different views available of the mechanism which is used for flapping a flat plate. So, there is a flat plate here which is made out of perspex, and it is going to be immersed in water. The water will be laden with tracer particles like glass globules, and then you will have a laser light sheet. You will have a camera or cameras looking at the light sheet, and there will be a synchronization like what you see over here, that the synchronizer receives command from the computer and it accordingly triggers the laser and the camera, and thereby as the plate flaps when it is immersed in water, it will displace the tracer particles in and around it, thereby creating a velocity field, and you are actually going to capture that velocity field using the PIV system. So, different parts of the entire setup is indicated over here. You have a vertical bar from which the flapping mechanism is suspended. The flapping mechanism's details, close up views are shown over here. So, there is a kind of a 4-bar linkage which helps you to achieve that reciprocating motion of the flapper. It moves up and down, and thereby it kind of churns the fluid around in its neighborhood. It is somewhat similar to birds' wings when they flap in air. And then you have a water tank. You have load cells which are mounted in that attachment which is carrying the mechanism, the flapping mechanism, so that when the flapping mechanism operates, the load cells can measure the forces which are acting. And once you fill the water, you have to adequately disperse the tracer particles so that it attains a kind of homogeneous dispersion. It may be difficult for you to understand over here because the image by and large looks very dark, but if you were to get a closer view, there are small particle specks which are actually around, because this liquid is now having the tracer particles which are illuminated with the laser sheet, and the illumination can be kind of made out because the laser sheet is also illuminating part of the mechanism. If you look at the different constituent elements of the setup in the actual location, then you can find them. You have the synchronizer here, the laser with the light sheet optics, and there is a kind of an arm which allows the laser to be positioned appropriately close to the model. Then you have the flapping mechanism over here, which is suspended using a vertical bar with the load cell on top. You can see two cameras focusing at that flow field, and if they are arranged appropriately at angular orientations, you can actually do a stereoscopic PIV, where certain amount of depth information can also be captured. So, it is not purely a planar, but also having a bit of the third velocity component incorporated. You have close-ups of the load cell and the DAC which is associated with the load cell. Once you perform the experiments, then you will get simultaneous measurement of the velocity field using your PIV system. So, you can now see this plate, the instantaneous location of the plate is indicated by that dark line, and you can figure out the velocity vectors here, which indicate the vortex dominated flow around the plate. The coloring that is done is based on the velocity magnitudes which exist. The red color region essentially indicates higher velocity magnitudes, and the next higher in strength is the green color, etc. This diagram indicates the time dependent variation of the normal force which is acting on the plate, which is essentially coming from the load cell measurement. So, you could actually do simultaneous acquisition of data both of the velocity field and the forces which are acting on the body. That helps you to also correlate between velocity field information and force information. Some more images over here, and we are also making reference with PIV images of flow past an airfoil that we saw earlier. You may recall that we showed a picture earlier where we had an airfoil installed in the wind tunnel test section, and that was a fixed boundary. We were not moving the airfoil boundary, and then we were capturing the velocity field in the leeward side of the airfoil where flow separation occurs. It is an unsteady flow because the separated region has a very strong time dependence, but that is not because the boundary is moving, it is because of the unsteadiness of the flow separated region. Here on the contrary, the unsteadiness is occurring primarily because the body boundary is moving within the flow field. The flow as such is a quiescent flow or a stagnant flow, but within that you have a moving boundary which is leading to the unsteadiness. So, you are essentially looking at PIV of a plate which involves a moving boundary problem, and performing PIV studies with moving boundaries is certainly more difficult than performing them on fixed boundaries. Additionally, if the moving surface is significantly flexible, let us say if this is a very thin plate which is deformable under the loads, then it will keep deforming as the loads change, and in that case tracking the surface geometry is quite a complex affair. It is a complex image processing problem. For rigid geometries, the instantaneous position of the boundary may be initially estimated from its kinematic equation, because you know what is based on the mechanism that you have devised, that what are the angular extremities of the oscillation of the plate, also what is the frequency of oscillation, etc. And then estimating the initial position of the boundary, you can then calibrate it with the flow field images. There may be minor variations with the ideal kinematic equation because of many reasons. The background color levels again indicate velocity magnitude. You see downward pointing arrow over here, and you also see a phi star. So, what do they indicate? The downward pointing arrow shows the instantaneous flapping direction of the plate, and the phi star indicates the phase angle. So, this plate will be moving down and then again coming back up. In this way it will keep reciprocating. So, you need to indicate that what is its angular orientation and in which phase of the oscillation it is in. Therefore, you can understand that moving boundary problems are far more complicated to tackle, whether it is an analytical method, computational method, or an experimental method. Here you see some more details of the setup where we are trying to convey this, that if you want to make this setup more flexible, where you can accommodate different types of flapping kinematics, you want to study different kind of motion modes of moving boundary problems, then you have to elaborate your setup further and further. And in order to have more control over the kinematics, you will have to have suitable arrangement for creating the desired motions and controlling them appropriately based on computer based control systems. So, here you have one where we have a couple of servo motors which control the movements of motors, of traverses, of cameras, etc. So, you have the servo drives which are controlling the servo motors. So, you have a couple of motors which are controlling movement along different axes. They may also be giving you rotational movement like this motor is doing. So, what it is doing is moving this belt to which a certain mechanism is attached and thereby inducing some motion into the mechanism. So, what we are trying to understand from here is that if you want to do different kind of motion modes, you need to have much more control over the way you manage those motions. Here you have a motion controller, a power source, etc. So, this is basically a pack which helps you to control these different motors, the traverses which carry the wings, which carry the cameras, etc. And that is all controllable from the software which you had at the PC end. Here what we are seeing is a subsonic jet and a cylinder wake with much more detailing of the flow field, because we are essentially looking at 3D flow field. So, you have an orifice from which a jet emerges, and as you move along the length, you see different structures emerging out of the jet, and there are structures which are breaking down, structures which are evolving, large structures, small structures, etc. A cascading of structures over here as you move further away from the orifice. So, this gives you a kind of a spatial development of a subsonic jet. It is a circular jet here. If it was a square jet or non-circular jet, then interesting happenings like axis switching, etc. can also be observed. So, this is happening through 3D PIV or tomographic or volumetric PIV. Similarly, here what you have is essentially a circular cylinder section which is facing a uniform flow and you are looking at it from top. So, it is a top view and this is basically the span-wise direction that you are looking at. You see that vortex structures have been shed from the cylinder. It is the Karman vortex treat that we talk about, and interestingly they do have a lot of span-wise variations. Not that the structures are completely two dimensional, they are highly three dimensional, and this is typically the nature that we see in turbulent wakes of bluff bodies. So, in tomographic or volumetric PIV, what we see is that the thickness of the laser sheet is increased using another set of lens to produce a volume which is much wider, say about 10 to 20 millimeter wide, which is significantly wider than the situation of creating light sheets when we try to do planar measurements. And this flow now has to be captured with many more cameras, at least 3 or 4, and pointing at the flow in different orientations, and the images that they independently acquire, they have to be suitably reconstructed, so that we can finally obtain the 3D flow field. So, it is a much more complicated process, but certainly doable. So, with this lecture we have come to the end of the discussion on particle image velocimetry for measurement of velocity field. In the previous lecture we discussed about materials and sizes of tracer particles, suitable lasers used for illuminating tracers, and light scattering characteristics of tracers. In this lecture we discussed on some more aspects of a typical PIV system like light sheet optics, cameras, cross correlation technique for velocity vector calculations, and the role of synchronizer. Subsequently, we looked at some experimental setups for PIV application. Thank you.